Hello, everyone. My name is Greg Risteman from Olympus. I'd like to welcome you today to this webinar titled Olympus Dual Linear Array Probe for Corrosion Imaging. This webinar will introduce you to the new Dual Linear Array Probe for corrosion inspection that provides advantages over conventional UT transducers used with flaw detectors. Our presenter today is Chris Magruder. Chris is the Phased Array AUT Manager for Olympus and has been developing and delivering phased array systems for over 12 years. He works with service companies and end users all over the world, providing phased array application development and support. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. The chat panel is not used for questions. If we are not able to get to your question during the live event, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Chris Magruder. Chris, take it away.
Hello, everybody. Thank you for joining us today. I see we have another good turnout with worldwide representation. We're going to talk today about a new DLA, Dual Linear Array Corrosion Probe designed for the OmniScan SX and MX2 for entry-level corrosion monitoring and erosion. The probe is a 7.5 megahertz 64-element probe optimized for pitch-catch 0-degree corrosion scans. So that means it has 32 elements on one side of the probe and 32 elements on the other side of the probe for a pitch-catch typical of 0-degree corrosion transducers used in both phased array and UT inspection. The element configuration is a 1 millimeter pitch in 2 rows of 32. The probe has an internal wiring so that it does not require the pulsar receiver or PR option on your OmniScan module. A regular pulse echo instrument is compatible with this probe. Any of the 1664 instruments, including the SX, is compatible with the probe, and it is designed with a mechanical roof angle, frequency, and aperture configuration to provide approximately 1 millimeter near surface resolution and a thickness accuracy typical of most phased array instruments without auto gain correction for about approximately 0.25 millimeters or 10/1000ths of an inch. The probe connects to the OmniScan with a regular connector and uses the standard OmniScan operating software. But unlike some of the other probes, 1D linear array probes typical of weld inspection and previous corrosion mapping, this has a fixed focal law or setup. So when booting the OmniScan, we boot normally and select MXU 4.1 R12 or later, and that's currently available on the Olympus website now. With the probe from the factory comes a USB flash card for files to be transferred to the user folder of your SD memory card. The corrosion probe is designed to be used with one of these pre-configured files for optimized beam size, and focal depth based on thickness. The default files provided are designed for carbon steel materials with a default velocity of 5890 meters per second. Other velocities or other types of materials are compatible with the probe and the OmniScan, and that's explained a little bit later. But the overwhelming majority of these applications are carbon steel. That's changing rapidly, but even today it's overwhelmingly carbon steel. The files are selected based on 3 criteria. The relative file that you'll need to drive your probe is first based on the OmniScan instrument. So that's either an first generation MX, a black, smaller type, non-touch screen OmniScan, the MX2, which is the blue base unit with a touch screen, or the new OmniScan SX. So depending on which of those instruments you have, we'll select the appropriate group of files. And then for the MX2, there's another group based on if your module is either the first generation PA1 or second latest generation PA2. And then within the three, for each of the possibilities, is a thickness range. The thickness range is a modification in the wedge delay and setup of the gate position and color palette relative for three ranges, of which the overwhelming majority of the thicknesses for corrosion mapping that we see at Olympus would be the 2 millimeter to 25 millimeter depth here. And again, these are copied from the USB flash drive that comes with the probe to the user setup folder on the SD memory card. This presentation is a condensed version of a 6-section full how-to series of presentations for the DL corrosion probe. All registrants that registered an email address will receive a download for the sample data files, the brochure of the instrument, or excuse me, of the DLA corrosion probe, and the full versions of each of those. So you need not screen capture them here. You'll get all of them and more in the download. So of the 3 files available, they come in fixed elements of 3, 5, and 7. As a 1 millimeter pitch probe, that's going to give us a virtual probe aperture of 3, 5, and 7 millimeters. Because these are fixed configuration files, this probe is not compatible with the setup wizard built into the OmniScan. It's dependent on modification of one of the default files for use. So the most common version of that, designed for 2 to 25 millimeter thicknesses, results in 28 independent A scans. And we can see that depending on which of the 3 you selected, it'll be a slight difference in coverage if you're measuring beam center point to beam center point within the probe. Upon loading the correct configuration file, the setup and use of the DLA corrosion probe is divided into several sections that have been condensed for this webinar. The first section for setup, we're going to do the UT configuration, the gate configuration, the C-scan configuration, and file save prior to data acquisition. These parameters will all be adjusted based on the thickness, surface condition, and then any different damage mechanism you should be looking for. But for the most part, the overwhelming majority of the applications for this probe are going to be hand scanning for thickness readings and corrosion backwall monitoring. Inspection of materials other than carbon steel requires a velocity to be calculated in the wizard through the OmniScan. So after the file has been loaded from the SD card, we're going to configure our UT parameters. One of the first things you'll notice about the corrosion probe is that there is no interface signal at 0 that typically inhibits near surface resolution and results in an interface signal right at 0 millimeters. This is true for all conventional and phased array probes that are transmitting from one side of the array and receiving on the other. Like a conventional UT probe, the benefit of that is to remove the surface echo that impedes near surface inspection for pitting and thin resolution, a better SNR, and it allows a mechanical focus inside the wedge for specific thickness. In most cases, setting the UT, it need only be long enough to cover the first back wall in most cases, and it's pretty common to increase the range for the second back wall, especially if a coating or paint thickness is needed to remove the reading, the coating from the reading. And that is also explained in the full version of the presentation. The range can be set from the UT general menu, or at any time you can tap on the touch screen on the first part of the ruler to set the UT start, and the second part of the ruler to adjust the UT range in full screen mode or in normal mode like we're in now. Adjusting the UT gain so that the back wall is between 100 and 200% amplitude will ensure that you minimize lost data points as a result of uneven surfaces and non-parallel orientation of the back wall, and it will give us a good reading. The amplitude on the back wall or general gain used for inspection must be adjusted based on current inspection conditions and will differ even between the reference standard or calibration block and the actual inspection, and most of that's due to the surface condition. The gain can be adjusted at any time by tapping on the gain area in the header or by selecting the UT menu general and gain here. This applies gain evenly to all of the A scans in the S scan. The gate mode is already configured for optimized inspection in the default files. It uses a first peak selection measuring edge. So within gate A, the first peak in the gate and the leading edge of that gate, right where my laser pointer is at now, is where the reading is taken. So because we're not using auto gain correction, the amplitude of that signal in gate position will have a slight effect on the thickness accuracy. Using the normal defaults under very typical conditions, 0.25 millimeter accuracy should be well within the range of the inspection without much optimization of the UT or gate position for the range of thickness listed for each file. The T reading is directly relevant to this inspection and is what we are looking at for the end result of our signal in the gate. And again, we'll also get an indication in the reading. In this case, we can see that the T or thickness reading is a function of gate A on the first peak edge mode, which is the recommended setting. Under the gate menu, we also adjust the thickness. This is a function designed for corrosion monitoring, and this allows selection of the source if you needed to change to include a B gate minus A gate to remove a paint coating, or if you had an application where you needed peak readings instead of leading edge, it could be adjusted here for the source of the reading, which will also be the source of the output for the C-scan data to third-party software. By default, it will set to the width of the gate, and it is reduced by the operator. The number that appears in the thickness reading will not be outside the range of what is listed in the minimum maximum range here. And it's normal prior to inspection conditions to set this from 1 to the nominal thickness and adjust it later during analysis mode or when inspection conditions are known. And again, the A scan we see here is VPA 28, which is on the far side of the probe on the S scan here. Every VPA or virtual probe aperture in the S scan here is made up of the individual A scans we see here, for those not familiar with phased array S scan or the OmniScan user interface. After the UT and the gate are configured, the color palette is configured. And again, we have another range here that by default will be the same as our gate thickness range, and a combination of the gate length and start position, the thickness entered under the gate, and the color palette, this will determine the color of our C-scan. Color equals thickness. And it's going to help us in the C-scan analysis to find our low spots quickly. It's normal to adjust the color palette both before, during, and after the inspection as conditions become known. The purple UT axis ruler is representative of the range selected, and then the color palette is scaled or applied over that. It can either be adjusted here directly on the C-scan right-hand column or under the display menu. Again, in the full version of this that'll be available in the downloads, we'll have individual sections for both sensitivity, wedge delay, and velocity calibrations. These are condensed here for the webinar for an overview and a couple key points, but there's a step-by-step with more information in the download available. The sensitivity calibration ensures that the A-scan amplitude across the first A-scan on this side of the probe here and the last A-scan on the far side of the probe here are equal or very close in sensitivity. The probe has a wedge that is integrated directly into the probe housing and cannot be changed. It's permanently coupled, so any loss of couplant or is a result of just the water or couplant under the probe and pressure. The A-scan only shows one A-scan or VPA at a time, so be sure and focus on the entire S-scan across. And again, the blue data cursor line here in the S-scan or tapping on the header for the VPA here allows me to change the current A-scan that's visualized inside the probe. So for the sensitivity calibration, a 10% amplitude sensitivity across the probe is the recommended setting. As you step through the wizard, if that is a requirement of your work procedure, when you're looking at the trace envelope in the sensitivity setting, and again, we see the focal law 1 or A-scan 1 from this side of the probe. This is the middle of the probe and the far side of the probe. This green trace represents the maximum amplitude detected at that time by each A-scan. So it allows us to see the amplitude of all A-scans. In this case, all of them are within 70 to 90%, which meets our 10% tolerance. When this case is true, it is not necessary to select calibrate, except can be selected here. It'll provide a green S that indicates either the operator modified or accepted the sensitivity calibration through the wizard. And again, that's more of the cases than not a procedural issue. For the overwhelming majority of users of this probe are going to be entry-level phased array in most cases with an SX, so the complexity of the setup and understanding of all the functions isn't necessary to be able to perform at a high level with this limited application. And again, an S as a requirement of having validated the sensitivity is a common procedural step we see in many procedures. The point I'm trying to make is you don't actually have to modify the sensitivity like in a weld inspection to be able to validate it. If the probe came from the factory and is within the specs on your probe certification sheet and has not been damaged, it would normally not require any calibration for sensitivity. In other words, if your coupling and pressure points are correct across the probe, and even we should easily be able to maintain the sensitivity of each A-scan on a flat block or reference sample or pipe sample at 10% of 80% across the whole probe. So wedge delay verification is also something that's a normal step prior to every inspection. And again, the integrated Rexolite wedge is permanently coupled to the probe and cannot be removed, repaired, or replaced. Minor scuffs and scratches, both on this probe or any even weld inspection probe, will not significantly affect the delay. Only significant wear that you can see is going to require a wedge delay on every single inspection. Care should be taken so that the guides are adjusted properly, either for flat or for piping, that we don't wear the Rexolite wedge or damage it unnecessarily. There's a very easy adjustment here. This is also made more clear in the full sections and the promotional video. The device loosens, allows the probe to be coupled to a pipe diameter and placed to provide support and stability for good readings. The wedge delay function is directly related to the accuracy of the thickness readings, which is what this inspection is all about. If you are using the wedge delay wizard, we want to enter a tolerance of 0.25 millimeters, which is the advertised accuracy of the probe. And again, that 0.25 millimeters is strictly based on us using a leading edge amplitude dependent reading at the gate leading edge position here. The thickness that we're going to use for the wedge delay calibration or validation should either be a reference standard with a certification of known thickness, or more commonly, especially if it's a velocity other than carbon steel, mechanical calipers that we measure ourselves the thickness. We want that to be a precise number, not a nominal thickness. So entering the wedge delay, select the good number, enter in the tolerance for the probe, and under almost all situations, if this is carbon steel and the velocity of your component is within about 50 meters per second of the default value for carbon steel in the OmniScan database, your probe wedge delay or thickness reading accuracy is going to be within tolerance all the way across the probe. In this case, it is preferable and highly recommended that you not select calibrate to readjust each A-scan's wedge delay, but simply select accept. The visualization of the 0.25 millimeter tolerance in the window for the thickness that the probe is on validates each of the A-scans across the array visually, and selecting accept prior to selecting calibrate, again, will give us our green W like a sensitivity, but it won't insert a course reading or velocity error into our inspection. No adjustment is typically required in carbon steel. If the wedge is actually worn, or if there's a slight velocity difference for your carbon steel making the thickness reading out of tolerance, the calibrate function is available, and this is done on one step or one thickness in the middle of the inspection range. This will bring the wedge delay into tolerance, but in this case exists on a normal carbon steel calibration block with a wedge and probe with no visible damage. You should suspect some other problem. Maybe the stabilization guide is not adjusted properly so that the probe is directly in contact well with the component. Under normal circumstances, we would not normally need to reset the wedge delay if the wedge is not damaged or worn beyond light scratches. So we would select accept, create our green W, and a wedge delay is validated. What's a more common and more useful step to validate both velocity and wedge delay is to do a dynamic clock scan of the step wedge or calibration block. In this example, I've set my gate over the area to include the lowest reading on the step wedge of 4 or 2 in this case, and long enough to include the thickest, which is 10. So whether you're in inches or millimeters, whatever your calibration reference standard is set for, you change the OmniScan that, and we'll take a quick look at a calibration scan in OmniPC. So in OmniPC, or on the instrument, I took a clock scan of the step wedge. I'm on a clock encoder, meaning that there's no wheel and the C-scan is moving at the speed of the pulsar. And I could take, for any lined down the step wedge, we can see 4 millimeters, 6 millimeters. So I'm 3/1000 of a millimeter out. Our advertised accuracy is 0.25 or 10 thousandths. 8 millimeters, which is about 8 thousandths out, and the 10 millimeter step wedge. And as I move, I can see each step from the dynamic clock scan. And I can save this and as a screenshot, or we can save the data file on the instrument or for our inspection reports for before and after the inspections. And it's a very quick way of performing the wedge delay and velocity validation, similar to as we would with thickness readings from a UT gauge. Standard similar function would be to use the ASTM flat-bottomed hole resolution block. This is a standard common calibration standard that you would see in any NDT supplier's catalog, and it contains a series of flat-bottomed holes of different size and different depth within the block. If I set the probe on the edge of the block, clear the C-scan and hit start inspection and take either a clock or an encoded scan of the ASTM block, we'll see a similar way of inspecting or preparing for an inspection as the step wedge. So this is a unit in inches. This calibration block is set up for inches for a 0.2, 0.3, 0.4, 0.5, and 0.75 flat-bottomed hole. If we set the reference and data cursor and measure cursor, we have a zone that's created within the cursor crosshairs, and we can see here is the 1.1 inch resolution hole, 0.2, and what I'm doing, I'm excluding the low flat-bottomed hole from the box as I check each one of them. There's the 3/1000 of an inch hole. Here is the 0.4 thousandths, and it's 3/1000 out. Here's the 0.5 and the 0.75. So by doing a quick clock scan and either saving it or doing a screenshot or just your own validation, it's a way of checking the linearity, the velocity, and wedge delay of the probe, either for one or all of the A scans. In this case, The A-scan is fixed, but I could put it in track mode and slowly walk it across the same calibration standard for a validation of each A-scan on each flat-bottomed hole for a validation of the thickness measurements. So what is the difference between a modern digital instrument and an analog solid state instrument with regard to horizontal linearity and velocity tolerance? A lot. The modern digital instrument can achieve precision and repeatability using a recalled file with a velocity that was predetermined in the software. That means if I were doing a job with 10 inspectors and I were using this instrument, I would expect all of them to have a slightly different velocity because it requires to be dialed in from a reference standard with a coarse reading. In an OmniScan job or any modern digital instrument, we are much more accurate and better off if everybody is using a standard velocity and we validate the readings without modifying the velocity of the instrument. And we see this a lot in both weld inspection and in carbon steel when Olympus support is often asked to troubleshoot data or repeatability problems. It normally comes back to a velocity error. So both of these would require use of a reference standard or step wedge. But again, entering the velocity and validating the reading is much preferable than a coarse velocity measurement where every inspector is using a slightly different velocity. So, true or false? Because the OmniScan or any phased array instrument has more A-scans and better software, use of reference standards is no longer necessary, right? Wrong. That is false. It is normal procedure in practice to validate readings on a step wedge or reference standard. Under normal circumstances, validation is possible without actually modifying the velocity or adjusting the delays. One of the benefits of using the standard default files for a fixed carbon steel inspection is that these things are already worked out and can be quickly validated. This will comply with any conventional UT procedure as well. To our knowledge, there are no codes or standards that actually make you adjust your setup from a wizard as opposed to validating the thickness readings, which is a validation of linearity and velocity and wedge delay. So is it possible that the velocity can be out of tolerance if 2 or more thickness readings on a standard step wedge are within the precision specified of 0.25 millimeters or 10 thousandths? The answer is no. If I were to check the step wedge here and here, and those readings are within tolerance, I can assume that the readings in between them are within tolerance, and that is not possible if the velocity were not close and the wedge delay was not accurately entered or predicted prior to setting it on the step wedge. So in cases where we do actually have to change the velocity, duplex, we're starting to see more exotic materials that are requiring inspection. Keep in mind that this probe is a 7.5 megahertz probe, so that's optimized for carbon steel. More attenuative austenitic materials might require a different frequency of probe. So if a velocity measurement using the wizard has to be made, it's made on one A-scan, and we do not use the nominal thickness of the pipe or plate. It could be out 10%, which would be normal. So we either want to use a reference standard made of the new material or use mechanical calipers to measure something prior to taking the reading so the velocity calculation will be correct. And in weld inspection or corrosion mapping, what the OmniScan wizard does, like every wizard similar of this type, it doesn't calibrate the instrument to a velocity. That's what the old UT analog systems did. What it does is it measures the velocity based on user input. And that measurement is done on one A-scan, one time, and it's completely dependent on the user taking the good measurement and the software knowing the real thickness of the component. That is the only way to get a new velocity other than carbon steel into the default setup files that come with the probe. Once the wizard steps are done with the new velocity, it adjusts the scale, it adjusts the UT axes, and the readings are then in tolerance with the new velocity. And again, there's a separate section within the presentation material you'll receive registering with this on each of the sensitivity, wedge delay, and velocity measurements, but keep it very simple. Under normal conditions, we would look at the step wedge, check it, a dynamic scan, save it, and move on to the inspection. So just to review up until now, we loaded a pre-configured file, we adjusted the UT, we did the gate configuration, we adjusted the color palette a little bit for our component, and then we validated the thickness readings and talked a little bit about each of the three types of calibration, the sensitivity, wedge delay, and velocity. When that's done, and I've saved the file and I'm ready to do an inspection, the next sequence is going to be to enter the part thickness, configure the encoder, we'll be in full screen mode, adjust to current situation on the component that we would not have known about prior, acquire the C-scan, and save and pause the data. This is very similar to all typical OmniScan applications, and it goes pretty quick with this application. So under the part thickness can't be known prior to entering in the configuration files, so it must be adjusted for each one. Under the probe part menu, under thickness, enter the nominal thickness of the part. You may or may not know it at the time of the inspection, and this can be changed in analysis mode at any time. This thickness here is going to affect our skip lines in the data, and it's also going to affect our material loss reading that we'll learn about. It's very simple math that based on the current thickness and the component thickness, the software calculates a material loss percent based on that. And again, it can be changed at any time before or after the inspection. Part thickness. The default configuration for the setup files is a scrolling time-based C-scan. That means that you see the C-scan building continuously, and it's not encoded, so it's not relative to the probe position at any time. It's just a visual indicator for the operator using color for thickness. If there's an encoder hooked up to the probe, or the probe is hooked up to a 1- or 2-axis in scanner, and the hardware comes with scanner ports typical of Olympus scanners and ports for the mini wheel encoder, this will synchronize the pulsar and the C-scan to the mechanical movement of the probe on the scan axis. Selection of encoder 1 here is going to change the time icon to a little mechanical wheel icon telling the operator that this is configured for recording all of the A-scans using a scanner or a wheel encoder. And we can see here that the typical mini wheel ports are built directly into the stabilization system around the probe. When a C-scan is selected, we'll also enter the start, end, and scan resolution. This will affect, on a clock inspection, how fast the C-scan builds left to right and how much data is buffered should you select pause and save data. For an encoded inspection, this defines the entire patch of the C-scan from the start to the end at a resolution of typically 1 millimeter. The OmniScan has a 300 megabyte file size limit that is dependent on these parameters, and the software will not allow a C-scan to be defined larger than this limit. But it literally is dozens of meters of scan time. It's a very small patch for this probe, and you should never reach the 300 megabyte file size limit under typical use. So once the probe is coupled well and scanned over a component, the C-scan is built. Both the pause and save data icons are available, or buttons are available right from the instrument to save the C-scan to the SD memory card. The size of the data file, the length of the acquisition visible, and the number of data points in the C-scan are all a function of the things we just looked at under the scan menu. Selecting unpause or deselect pause will activate the C-scan and continue inspecting. So when you're either on a clock inspection and you've acquired a piece of data, or you're on an encoded inspection and you've taken the entire C-scan depth or length, select pause and save data, and the data is on the flash card, and it can be analyzed either directly on the instrument, offline using OmniPC, or converted to TomoView for more options for the C-scan and the C-scan export. Real-time analysis on OmniScan recorded data file for corrosion mapping requires 4 basic functions. The first is the C-scan optimization. We're going to adjust the color palette and reposition the gate if needed for general screening. Often during the inspection, we encounter problems that were not necessarily known prior to inspection that we would want to move the gate position and optimize the color palette. We're going to use the A-scan and S-scan for individual data point analysis from a color pixel in the C-scan. We're going to use the data cursor for individual data point thicknesses and material loss readings. And within the cursors on the C-scan, we will create a zone for zone minimum thickness and location. So the probe face in a single line scan represents the A-scan first to A-scan last stacked vertically. This axis at 28 millimeters represents the entire length of the probe using the 5-element configuration. And the green vertical ruler for a 0-degree linear scan is volumetrically corrected, so it's millimeters to millimeters, whereas in an angle beam inspection, those of you that do OmniScan, an angle beam shear wave weld inspection, would normally be seeing the C-scan in focal laws or apertures here. This is in real millimeters. That's possible only at 0 degrees. And the blue ruler at the bottom of the C-scan represents the mechanical movement of either the probe on time-based inspection or with a wheel encoder 1 millimeter at a time. The color is going to be our immediate reference in the C-scan for problem areas, low spots, and the nominal back wall. When we configured our color palette a few slides ago under Properties, we configure it for a 1 to 12 millimeter, which was the nominal thickness of the component. With this condition, the color palette is going to generate a blue pixel here at 12 millimeters and a red pixel at 1.25 millimeters. As I adjust these numbers or move this on the touch screen of the instrument or with a mouse in OmniPC, the contrast of the C-scan is going to change to help me find the low points in the data or the problem areas of whatever I've just scanned. When I place the data cursor over an area here with no corrosion, I can see the 11.97 millimeter reading, which was taken at the leading edge of gate A here. Okay. It's a 0.2% material loss, and we can see the color associated with it is a dark blue. As I start to change that and move it either directly in the software 1 millimeter at a time, or by taking my mouse or finger on the touch screen and dragging this up, I'm going to change the contrast of the color palette until my first red pixels appear in the data. In this case, going from 2 millimeters to 3 millimeters, I can see the pixel turn to red. So I know I have at least one data point between 2 and 3 millimeters and no data points less than 2 millimeters in the C-scan. Okay. I'm going to continue doing that until we see areas of corrosion of severe, either a single area or several areas. As I'm increasing this color palette range or reducing the color palette range, I'm scaling the color over my thickness as an indication of where trouble spots are. This might be an isolated pit or something that contaminated the gate. This looks like a more realistic area of corrosion. I'm just doing this on the C-scan first without the benefit of the A and the S scan. Once we're on the A and the S scan, and again our views are available from the layout here, either in normal or full view, we'll see the side and in views of the data. As the C-scan changes size based on the size of the window, if a C-scan is created that contains more data points than the number of pixels available on the C-scan display, a red C appears in the header indicating that the C-scan is in a compression mode. In a compression mode, it means that 1 pixel on the display can represent 4 or 16 data points in the file. And the compression mode ensures that the most significant data point, which in corrosion would be the thinnest, is always represented by the color. And as I zoom in or change displays to a larger C-scan, eventually that C goes away. This is blind to the user and only a visual indicator. It requires no configuration. It's just a visual indicator to be aware of the compression of the C-scan. The 2 natural views for analysis available in the OmniScan SX and NX2 are the A, S, and C-scan layout, and as pictured here, the A, D, S, and C-scan layout. So in our C-scan, with the crosshairs on my little pit here, I can see it in the side view S-scan, the end view B-scan, and I see the A-scan representation that generated the low red pixel in the gate. So A-scan and S-scan analysis is done by using the blue data cursor on the C-scan. Even in areas where we have a white pixel indicates a no detection in the gate. But we can still see by A-scan and S-scan analysis where the river bottom or back wall is in the corrosion. I can readjust the gate to try to acquire those data points, but it would normally contaminate the rest of the C-scan, or I'll use the A and the S-scan to make any notes and have an understanding of what's happening. Again, color represents thickness, and we want to manipulate the color palette so our red worst areas are just visible in the thickness range of the data points inside the C-scan. The S-scan characterization is what will enable us to identify and size other failure mechanisms other than backwall corrosion erosion. And those include small pits, hick, creep damage, nick, many other types of failure mechanisms in addition to just back wall geometry and laminations using the A-scan and S-scan. This blue data cursor on the C-scan represents the aperture inside the probe. This would be the front of the probe. This would be the back of the probe. And this axis with this cursor represents the mechanical movement of the probe on the direction of filling the C-scan. So in the three pre-configured files, they are also pre-configured using the Corrosion Group 2 of the default OmniScan's readings database. This gives us 4 readings in 2 groups, 8 total readings to include typically what's necessary for a corrosion inspection. On any single point, we'll see the T reading, the material loss, and the amplitude. And we have another group of readings in group 2, or excuse me, before this, a little bit more about the material loss here. Ultimately, that's what the end buyer wants to know about his inspection is how much material is lost. So of our 12 millimeter thickness, the T reading in the gate, based on the gate configuration used to measure it, gives us a 77.5% material loss. Pretty simple math. And then we have a series of readings on the second group of 4. And again, on the touch screen, toggling this area on the touch screen or with a mouse in OmniPC will switch between the 2 groups. All of the readings that include a Z means they're relative to the zone. The zone that's created, similar to how I validated the thickness readings using the ASTM calibration standard I demonstrated earlier. If I create a zone with the crosshairs of the 2 cursors on the C-scan, within the zone, I can see that the lowest reading was 5.96 millimeters, and it occurred at 22 by 6 millimeters on A-scan or virtual aperture number 6. And I could go look at that individual data point. By creating the cursors all the way at the extremities of the C-scan, I can see the low spots for the entire C-scan. Again, through the course of the series of presentations, there were several data files used, including the reference standard blocks. If you're an OmniPC owner or an OmniScan owner with 4.1 or later in the current version from the Olympus website, you'll be able to reproduce these same readings and data points and images directly from the files that are included in the download that reference the presentation's full versions. And again, in that download will also be included the brochure for the probe that also includes more specific information for the specs and the limitations on the diameter sizes, ordering information, and the data files and a full presentation from which this presentation was a condensed form. So we're going to end it there for this session. I want to thank everybody for joining us. I'll turn it back over to Greg Proctor.
Thanks, Chris. Nice job. On behalf of Olympus, I'd like to thank all the attendees for joining us today and Chris for his expertise and participation in today's event. We hope the material presented was informative and useful. This webinar, along with a Q&A session, will be archived on our website at www.olympus-ims.com. Everyone who registered for the event, whether you attended or not, will receive follow-up email with links to the archived presentation, data files, brochures, and etc. A nice little package coming down. That's going to do it for today. Thanks again for attending, and we'll see you all again next time.